Welcome to the viewers. Now we find the derivative of the Laplace transform. What is it? If gt be any function which is piecewise continuous in any finite interval of t and is exponential order of e to the power at t tends to infinity, then Laplace transform is differentiable at any number of times. It's a conditions, but we write simply the result, not the rigorous analytical treatment. We just write the result and just easily prove it. That means if we condition here GNP, that means nth order derivative of Laplace transform. If GP be the Laplace transform of GT, if GP be the Laplace transform of GT, then its nth order derivative, that is GNP, which is given by -1 whole to the power n L of Laplace transform of t to the power n gt, and which is for the region real p greater than n. This is a conditions, but we simply prove it without rigorous analytical treatment for real p greater than some constant a. That's the exponential order of e to the power. That means it's a conditions, not required. If gt is piecewise continuous and gt is exponential order of a, gt is e to the power at at t tends to infinity. That's why this a will come. Now at first, from the definitions, we know gp be the Laplace transform of gt. So by definition we write in 0 to infinity to the power minus pt. P is the complex parameter we already know, gt dt. Now if we are derivative, simple derivative g dash p, so with respect to p, and partial derivative exists del p of these functions, and since it's complex, so it has two parts. That's why one part is x plus iy form. So here we find the partial derivative, not total derivative. So simply if we are taking the derivative, partial derivative with respect to p, and actually in the complex part we mix in two separated real parts connected with the special sign I is equal to root over -1. But here we already removing all the complex approaches, we are doing it simply. So taking just derivative with respect to p, partial derivative. Now it will be clearly minus t to the power minus pt with respect to p, so it will be treated as constant gt dt, and simply we write here -1 0 to infinity t to the power minus pt gt dt in this way. Now by proof of the method of induction, simply g dash p, here it will be t, and so it's clear by GNP, so it will be treated as whole to the power n, and 0 to infinity up to t to the power n e to the power minus pt gnt dt, and which also exist in the same real domain, real p greater than a. And if we prove it here gn plus 1 p, so it will be clear as -1 whole to the power n 0 to n t to the power n plus 1, and it's also have after n steps, and it will be proved by n equals to m plus 1 if we are taking it in this way. That means e to the power minus pt gt dt. If we take it here m, for that means m is equal to n plus 1, we get g to the power mp, that is m 0 to infinity t to the power n g to the e to the power minus pt gt dt. So it's already clear and already exhibit this result is true for n equals to m plus n. So by induction method of induction, we can say GNP, that will be equals to minus 1 whole to the power n, 0 to infinity t to the power n e to the power minus pt gt dt, that will be minus 1 whole to the power n Laplace transform of t to the power n gt. It's clear, and exists for a real p greater than a if gt is exponential of order e to the power at, a be the constant. So in this way we can find the important result, and we know, and we came to know how to find the derivative of Laplace transform. In the earlier case, we find the Laplace transform of the derivative of a function, but here we find derivative of the Laplace transform. That means g dash p, and finally we find GNP of nth order. That's why GNP. In this way we can find. Now it is helpful in solving many important problems. That's why we give some of the glimpses of ideas, and in many cases of inverse type Laplace transform problem, we needed to apply this type of theorem as working rule. Thank you.